Welcome back to Vuln Vibes. In this episode, we're going to talk about Gogs vulnerability.
Yeah.
And this is a really critical deep dive, especially for anyone out there managing self-hosted source code infrastructure. We're not talking about some theoretical bug here. We are dissecting a fresh, actively exploited zero-day that has, well, it's punched a massive hole in the defenses of thousands of organizations using Gogs.
That's absolutely right. For our listeners who are, on the front lines of incident response, the identifier is CVE-2025-8110. It's a vulnerability in Gogs, which is a super popular lightweight Git service, and the severity is, well, it's as bad as it gets. Remote code execution?
RCE.
Yep, RCE, achieved through what is basically a symbolic link path traversal bypass. And the most important part is this isn't just a paper, it's being used in the wild right now.
So our mission for this deep dive is threefold. First, we're going to unpack the exploit chain. How does a simple symlink actually lead to full RCE? Second, we'll get into the threat actors methodology, which seems to be highly automated and, frankly, shockingly successful. And finally, we'll detail the immediate mitigations you need to deploy today because the data suggests over 700 instances are already showing clear signs of compromise.
The urgency really can't be overstated. When you see numbers like that in a live campaign, it means defenders have to be in two modes at once: forensic investigation and immediate hardening.
Okay, so let's start with the backstory. I think it's fascinating because the discovery of the CVE was, completely accidental.
It was, yeah. It really speaks to the value of just, good old-fashioned threat hunting. The Wiz Threat research team, they didn't find this by scanning code. They found it while cleaning up a totally different mess.
So they were already on a compromised machine.
Exactly. It was a routine forensic job after some malware investigation, standard cleanup, patching systems, checking for persistence, all the usual stuff.
And what was it that made them stop and go, wait a minute?
Well, they found a compromised machine that was running a Gogs instance. But here's the critical detail. The version of Gogs on that server was supposed to be secure. It had been patched against all the known path traversal bugs, including a very recent, very similar one.
But the server was still owned.
Undeniably. So that immediately tells you that the patch didn't work, or more likely, the attackers found a way around it.
A bypass.
Precisely. The evidence of compromise on a supposedly patched environment just forced them to realize that a whole new, unknown bypass vector was being actively used. It's a huge lesson, right? A patch fixes one specific flaw, but the entire class of vulnerability, in this case path traversal, often remains open to clever new approaches.
And Gogs is so popular because it's lightweight and easy to self-host. Thousands of orgs use it for their private code, which means the stakes here for IP theft are massive.
It's a very, very target-rich environment.
All right, let's pivot to the technical side, the mechanism itself. Because this flaw, CVE-2025-8110, is a direct bypass for its predecessor. So where did the original patch go wrong?
It's a textbook case of what we call a canonicalization failure. So when the developers fixed the first bug, they focused on validating the input string.
Meaning they checked the file path for things like rate not to stop directory traversal?
Exactly. They put in checks to make sure any file writes were happening inside the repository's root directory. Sounds good, right?
But the file system has other tricks up its sleeve.
It sure does. So the input validation was doing its job, but it completely failed to account for symbolic links, symlinks. The vulnerability is that the Gogs API takes a file path for a write operation, but it skips the most crucial step. It never checks if that target file is actually a symlink pointing somewhere outside the repository.
So the security check looks at the path the attacker gives it, says, yep, that path is inside the repo, looks safe, and then it just hands that instruction off to the operating system.
Which then happily follows the symlink to, say, a critical system file somewhere else on the disk. The API trusts the logical path, not the final actual canonical path that the OS resolves.
And what makes it so dangerous is the low barrier to entry.
Trivial. An attacker just needs permission to create a repository. That's it. Which, as we're about to see, is often the default setting.
Let's walk through that exploit chain. So I'm an attacker. I have an account. I can create a repo. What do I do next to get RCE?
Okay, so the first thing you do is commit a specially crafted symlink into your new repository. And this symlink is designed to point to a very specific sensitive file outside of the repo's root directory.
What's the target? What are they going after?
The main goal is to manipulate the Git hooks on the server side.
Okay, for anyone listening who isn't a Git admin, what's a Git hook and why is overwriting it so bad?
A Git hook is basically just a script Could be Bash, Python, anything that Git runs automatically on the server when certain things happen. Like there's a pre-receive hook that runs before a commit is accepted and a post-receive hook that runs right after. If you can overwrite that post-receive hook with your own malicious script, the next time any push happens to that repo, the server will execute your code with the permissions of the Gogs user.
Got it. So the symlink points to the hook file, the API blindly writes the attacker's malicious script to that hook file, and boom, the next Git operation triggers the payload, RCE.
That's the whole chain. It's clean, efficient, and requires almost no user interaction, which makes it perfect for automation.
Which brings us to the active campaign. Researchers are calling this a smash and grab. Automated, aggressive, very noisy. What does that tell us about the actors?
It suggests they're opportunistic, not spies. This isn't a quiet, targeted espionage campaign. This is about hitting every single exposed target as quickly as possible, probably for botnet resources or just to establish a broad foothold before everyone patches. It's a numbers game.
And the numbers are just staggering. The research team scanned 1,400 exposed Gogs servers. They found over 700, that's more than 50%, showed clear signs of compromise.
That 50% figure is a huge alarm bell. It tells you one of two things. Either an overwhelming number of Gogs admins use insecure default settings like open registration, or the exploit is just so reliable it works almost every single time. Probably a bit of both.
So what are the key indicators of compromise? What should admins be hunting for right now on their systems?
The artifacts are pretty distinct. You need to be searching your Gogs logs and database for any newly created repositories with random 8-character names. And this activity is very time-bound. Most of the compromises they saw were clustered around a very short window starting July 10th. If you see repos like that, created around that time, you have to assume you're compromised.
Now, what's interesting is that while the exploit is simple, the payload they're dropping is actually pretty sophisticated.
It is. Once they get RCE, they deploy a pretty robust command and control, or C2 mechanism. The malware is built using an open source framework called Supershell. And this isn't just some basic script. It establishes a persistent reverse SSH shell back to the attacker.
Which gives them full, persistent remote control. They can come and go as they please.
Exactly. It turns a quick smash and grab into long-term persistence. They can move laterally, steal source code, use the server for other attacks, anything.
And they're trying hard to hide this payload from defenders. What kind of evasion techniques are they using?
They're using some heavy binary obfuscation, which points to a group with, a decent level of operational security. The sources highlight two main tools. First is a Go-specific tool called Garble. Since Gogs is written in Go, this is a smart choice.
Why is Garble so tough for security analysts to deal with?
Because Go binaries naturally contain a lot of metadata. Garble just shreds all of it. It randomizes class names, function names. It makes static analysis a nightmare compared to a standard C binary.
And they're layering something on top of that, right?
Yes, on top of that, they're using standard UPX packing. So you have this Go binary that's first been scrambled with Garble, and then it's packed with UPX. The end result is that almost all the useful string literals like C2 domains, commands, error messages are encrypted on disk. It seriously slows down anyone trying to figure out what the malware does.
Okay, so this is a high-priority incident. Let's move to the most important part, mitigation. We know that as of today, December 1st, 2025, this is a live 0-day. There is no official patch. Waiting is not an option. What do admins need to do right now?
First thing, break the exploit chain. You have to remove the attacker's initial entry point, which is the ability to create a repository. If your Gogs instance has open registration enabled, allowing anyone on the internet to create an account, you have to disable that. Immediately, that one change cuts off the primary attack vector.
Okay, that's access control. What about the network side of things?
Network segmentation. This service really shouldn't be on the public internet if you can help it. The strong recommendation is to put your Gogs instance behind a VPN. If you can't do that, at the very least, lock it down with a strict IP allow list. Only your office IPs, your CI/CD runners, trusted sources. That's it. Shrink that attack surface.
And for those who suspect they're already hit, what's the hunting strategy?
Don't just rely on your antivirus to find the C2 binary because it's so heavily obfuscated. You have to proactively hunt for those IOCs we mentioned. Look for those weird repos with the random 8-character names created around July 10th. Dig through your logs for evidence of symlink-right operations. That's the real smoking gun.
You know, this whole incident really shines a light on a much bigger problem, which is just how hard it is to truly fix past traversal bugs.
It really is. This 0-day shows the gap between simple input cleaning and proper, robust canonicalization. A real fix isn't just about stripping out from a string, it's about resolving the path to its absolute final form and then checking if that final destination is safe. If the canonical path is outside your sandbox, you kill the operation. Period.
Right, because things like symlinks or FIFOs or device nodes, they introduce these redirection vectors that a simple string check is always going to miss.
And that one oversight is what turns a patched vulnerability into a critical RCE 0-day.
So that brings us to our final takeaway. To recap, CVE 2025-8110 is active RCE. It's a trivial symlink bypass. Attackers are using the obfuscated Supershell C2 for persistence. Your immediate actions are to disable open registration and lock down network access.
Time is absolutely of the essence. You need to be looking at these systems now.
So here's a final thought for you to mull over. Given that so many 0 days come from these kinds of patch failures, where a fix for one bug just creates another, subtler one, how radically do we need to change security auditing? Should we be dedicating more resources to just analyzing the diff of a patch, specifically hunting for ways that other file system objects, like symlinks, could bypass the fix? It's a fundamental question about how we approach secure design in a world where the first patch is often not the last word. Thank you for joining us for the deep dive.